Welcome to Homework Lib.
Okay, so we're doing chapter 34, problem 101. Okay, so this problem talks about a zoom lens, and it's pretty complicated here, but the picture's in the book here, and it says the converging lens has a focal length of f1. Okay, and the diverging lens has a focal length of f2 that is less than 0. Two lenses are separated by a distance d that is always less than f1. It also tells us the magnitude of the focal length satisfies this inequality. Sorry, is greater than f1 minus d. Okay, so to determine the effective focal length of the combination, consider a bundle of parallel rays radius r0 entering the converging lens. Okay, so let's go ahead and draw that. So imagine we have this lens here. We got a bundle of parallel rays at radius r0 entering, and these get converged to some point here. And that should be f1. We know there's some point D in here where the other lens is. So this is where it would enter the other lens. So this would be what we define as R naught prime. Okay, so what we want to do for part A is we want to show R naught prime can be described by the equation they give. So to do that, we're going to look at this and think about similar triangles. If we zoom in where the lens is, we should have one triangle here with the distance f and r naught, and we should have another distance here with f minus d, and this being r naught prime. So if we just relate these with similar triangles, we know that r naught over f1 equals r naught prime over f1 minus d. Let's rearrange that and solve for r naught prime, and we get r naught times f1 minus d over f1, which is exactly what they wanted us to show. So that was easy, just the similar triangles there. Okay, so let's move on to part B here. So part B is saying, show that the final image I prime is formed at a distance that. Okay, so to figure out what the final image is going to be, we first know that, let's see here. So we know that the image is formed at a distance f1 minus d to the right of the second lens. So from this, we can, sorry, this is the image of just the first lens, right? From what we did above. So the image of just the first lens is formed at this. And now we can rearrange that to the object distance for the second lens. So this is going to be given as, if this is to the right, we just have to make this negative, right? Which is the same as flipping this. Okay. So now from this, we can use the thin lens equation, and we know S2 prime is S2 F2 over S2 minus F2. So we can start plugging stuff in here, and we see that this is D minus F times F2 over D minus F1 minus F2. Cool. I'm going to add a new page here. Let's rearrange that. We also know that F2 is less than 0, right? So we can also rearrange this to say S2 prime is F minus D times the absolute value of F2 all over absolute value of F2 minus F1 plus D, which is exactly what we needed to show. Awesome. Let's move on to part C here. So for part C, we want to, let's see, where is the page? Okay, so if the rays emerge from the diverging lens and reach the final image point are extended backwards to the left of the diverging lens, they will eventually expand to the original radius R0 at some point Q. So the distance from the final image I0 to the point Q is the effective focal length of the lens combination. If the combination were replaced by a single lens of focal length f placed at Q, parallel rays would still be brought to a focus at I prime. Show the effective focal length. Okay, cool. So from this, let's draw the effect of just these on the diverging lens. So if we have our diverging lens here, we know these enter like this, where this is a distance R0 prime and this is a distance R0. And they get focused somewhere over here that we call I prime, where the image is. Okay, so this distance from here to here, we call it S2 prime. Cool. So from similar triangles in here, we should see that, oh, sorry, this is all F, the focal length. So we know that this over F is similar to R0 prime over S2 prime. Cool. So let's combine this, or let's rearrange this, right? So R0 over R0 prime equals F1 over S2 prime. If we combine this with what we found from the first part, we know that this is F1 over F1 minus D. Sorry, I was writing F. This is an F. This is the effective focal length, right? So I'm going to write FE just so I don't get confused. Cool. So now we can just rearrange this, solve for the effective focal length, which then becomes F1 S2 prime over F1 minus D. And if we plug in what we got for S2 prime, we can then simplify it even further. So I'm going to move up here. So we know that FE now is, well, the F minus D's are going to cancel. So we should be left with F1 magnitude of F2 all over magnitude of F2 minus F1 plus D. And that's exactly what we needed to show. Perfect. Flying right through. Okay, we have one last part D here. So part D says, show the effective focal length, oh no, if F1 equals 12, so F1 equals 12 centimeters, F2 equals negative 18 centimeters, and D is on the range between 0 and 4. Find the maximum and minimum focal lengths of the combination. What value of D gives F equals 30? Okay, so D equaling 0, immediately we should see that F equals 36. Plugging everything in. Awesome. Oh, sorry, let's actually plug this in. So this is 216 squared over 6 plus D. That's with all these numbers in. So now we have FE only in terms of D. Awesome. So now if D equaling 4, the maximum, we can see that F then becomes 21.6. So this is F max. This is F min. All in centimeters. Cool. So now for F equals 30, this is 216 squared over 6 plus D. We can just solve for D. And we see that D then is 1.2 centimeters. Perfect. That looks like that's everything.